Welcome to ASTR 103, Astronomy. I will be your professor of record, and that is Dr. Rob Parks. I will thoroughly introduce myself in lecture tomorrow. The way that this course is going to be set up is that it's going to have an inverted shape in the sense that I will record lectures offline, post them to my YouTube channel, where you will watch them in the comfort of your own home. And then in class, I will go over basically the highlights of the lecture, and the rest of the lecture time will be dealt with in-class activities. It's going to be much more of an active learning process in the lecture environment than it would be ordinarily. One of the things that we will also be doing in class are lecture quizzes. And so I will start off each of the classes with 2 or 3 quiz questions related to the lecture material that were posted on YouTube. So a couple of things to note there. One, before the beginning of class on Wednesday, please make sure that you have Top Hat material or the Top Hat software, and that you come to class early so that you can actually be present when those questions are being asked. If for a university-sanctioned reason you need to miss a class, please let me know as soon as you can, and I can make arrangements for you to make up the questions that you missed. The other thing I wanted to note before we get into the lecture itself is the Discord. Hopefully you have all gotten the Discord link. If not, please email me and I can give you a refresher link. I have set up a Discord channel so that I can post announcements. Students can communicate with each other. You can communicate with me. I will be hosting virtual office hours as well as office hours in class, or in my office rather, during that time. And so I will be using Discord fairly extensively, as well as Blackboard throughout this course. So please, if you have not already done so, join the Discord server. And when you do, please let me know which class you are enrolled. That way I can give you the appropriate access. For today's lecture, we'll be talking primarily about light and how light is used by astronomers to determine pretty much everything that we know about the universe that surrounds us. I hope you enjoy. Okay, first lecture of the semester. Yeah, always fun. All right, so let's get right to it. Howdy all. So I have been teaching astronomy for a while now, and I've seen a number of textbooks and a number of different ways of teaching the subject, and I've always been somewhat disillusioned with how it's done, or at least in how it starts off, because typically the textbooks and instructors would like to wow you and dazzle you with the fact that the universe is really, really big and really, really old and other incomprehensible things like that. What I want to do, I want to start off more of a narrative in the sense of how is it that we know anything? How is it that astronomers who can't leave, pretty much for the most part, cannot leave the surface of the Earth, certainly have never in person left the orbit of the moon or beyond the orbit of the moon. How do we know anything about, say, galaxies that are millions upon millions of light years away? And the answer to that question is light. Let's see, that didn't work. How about that? Aha! Yay! All right. So the overview of this lecture will be that we'll start off with talking about the fact that the universe is really super big, and the fact that the only way, pretty much the only way, 95%, and that's a completely made up number, but it's in the ballpark, 95% of what we know in astronomy has been derived from the capture, manipulation, and analysis of light. Now, there are certain aspects of astronomy that can be done in the lab, particularly if you really love the exciting field of dust. You can literally build dust molecules or dust particles in the lab and shoot lasers at them and see how light refracts off the surface, which you get to play with lasers. So I'm going to have to reevaluate my thoughts on dust. Anyway, lots and lots of my point is there's a very small subsection of astronomy that can be done in a controlled laboratory setting. Everything else must be done using a telescope of some sort, as I said, to collect light. We will discuss the properties of light, what exactly is light, and we will study patterns of light known as spectra, which provide a great deal of that 95% of our knowledge. Pardon me, my glasses are dirty. So, features of light. What is light? What is light, and what can we say about it? And surprisingly, when it comes to how ubiquitous light is, physics is a little bit confused as to what it actually is, what it physically, or how to physically represent it. The way that I like to think of light is that light is energy transportation. Light moves energy from one location, point A, to point B. And that's pretty much it. And in doing so, communicates changes in that object and what that actually object is. The reason why we know visually what the universe looks like is because light is communicating that information to us. And that is going to have real consequences when we start talking about things later on down the road, like relativity, black holes, the universe itself. When we look far away, we're not looking at things as they are now. We're looking at things as they were millions upon billions of years ago. And to be perfectly technical, everything that you see around you is delayed. You do not perceive the universe as it is in this moment. What I mean by that is because light has a set speed, it takes a small amount of time, depending on the distance, for that light to hit us. Now, light in this room, it's pretty much instantaneous, but it's not technically instantaneous. This room, I perceive this room as it was, petaseconds ago, or however long it takes for light to get to us. The sun is 8 minutes away, which means if Thanos were to snap his fingers and make the sun go away, we wouldn't know for 8 minutes. And when I say we wouldn't know, what I mean is, we wouldn't be able to see it. We would still see the sun happily burning away for 8 minutes, and B, we would still feel its gravitational influence for 8 minutes until that information got to us. This is the kind of stuff that I think about late at night when I can't sleep. Anyway, so this idea of light, this idea of this communication of energy from point A to point B, how is it best described? And we've been talking about this. Physicists and astronomers have been debating this for hundreds of years at this point, pretty much since Newton, and actually a little bit before him. And at this point, as far as I can tell, we just kind of, Pontius Pilated and just kind of washed our hands of the idea, and we're just, it's both. And what I mean by both is that the light can be described either through wave theory, basically the idea that light propagates as a perturbation of electromagnetic waves, so it pretty much looks like the surface of a lake. Once you perturb it in some way, drop a pedal in it, jump into it, what have you, waves that we normally associate with the ocean. That's what light looks like, or at least folks like Huygens would have you believe that's what light looks like. Newton, on the other hand, believed that it was actually more corpuscular in formation, which was which pretty much got ignored up until the 1900s when Planck was like, no, maybe Newton had some idea, was onto something. That light was in fact actually quantized. It was little bits of information that had discrete packets of energy that were carried along, that traveled through space. Einstein won his Nobel Prize not for relativity, but because of the photoelectric effect, which is best described using this photon or corpuscular theory of light. As it happens now, it's really which makes the math easier. How best to describe light? If you want to do something like the photoelectric effect, if you want to study, say, solar cells, then it makes a lot more sense conceptually and mathematically to look at light as if it's a particle and not a wave. But if you want to understand how say, the Young's double slit experiment, where you have light interfering with itself, that is best done with a wave, because again, we now have the capability to actually shoot out light one photon at a time. And so the idea that a photon could pass through two slits at the exact same time, that kind of boggles my mind. Again, much easier to think about, much easier to deal with mathematically by thinking about it as a wave. So, pick your poison. But the key thing, though, with light is that it is an energy transport mechanism. It tells us, it transports energy from one point to the next and tells us about it. For the purposes of this course, we're going to pretty much keep with the wave motion of light until we talk about spectra, and then we're going to delve into the idea of photons to a certain extent. But for the most part, we're going to keep with the idea that light is a wave. It's the easiest way to really describe this. And as I said, it's a wave. This type of wave is known as a transverse wave. It goes up, it goes down, it goes up, it goes down as it propagates from left to right. Very much like a guitar string or Dude Bros CrossFit ropes or waves on water. And so the idea here is that particles in the wave move up and down as the wave moves through them. So a leaf, for example, on the surface of the water, for the most part, as a wave propagates through it, the wave is going to oscillate up and down. It's not going to get any closer to the shoreline or further away. And so there are a few properties of light that we can talk about when we talk about it in terms of a wave function. Now, two of which are the amplitude and the wavelength. You can think of these as the height and length, characteristic height and length of a wave. Now, amplitude, like I said, is the height. You can pretty much just ignore it because we're really never going to talk about it again. It's akin to the intensity of the light. It's basically how bright or how big the wave is. But we're really never going to address that again, particularly in terms of amplitude. Wavelength we're going to be talking about a lot. Wavelength is one of the key characteristics of light. Via wavelength, you can directly tell the amount of energy that light is carrying. And the wavelength, again, is the characteristic length, and you can measure that any number of ways. Basically, from one point to the same point over to the next wave over. So like a peak to a peak, a trough to a trough, but again, same point on one side to the same point on the other. But just to simplify it, the wavelength is the distance between the peak of one wave to the peak of the next wave. Then we have frequency. Frequency is the commensurate characteristic to wavelength. Frequency basically tells us how many waves pass by a particular point in space every second. Now, if we were talking about any normal wave, like earthquakes or a ripple along, say, a slinky or what have you, then The frequency and the wavelength are not, pretty much not really, well, they are correlated to the velocity of the wave or what have you. Because what I'm getting to is because light is ultimate speed limit, it is a constant. What that tells us, if we know the wavelength, then we also know the frequency. If we know the frequency, then we also know the wavelength just right off the bat, because again, we know what the speed of light is, and we know what the speed of light is through various mediums. So if you don't know what the speed of light is through water, you can pretty much easily look it up and figure it out. So again, frequency is the number of waves which pass by a particular point, and it is measured in hertz or cycles or peaks per second. So for example, 60 hertz would correspond to 60 waves passing by a point every second. Or in terms of refresh rates, if your television has a refresh rate of 60, you probably need a better television, but that means that your screen is refreshing at once 60 times every second. So again, the key representation here is that the velocity of the frequency of the wave times the wavelength of the wave equals the velocity of the wave. But again, because we know that the speed of light is a constant through a medium or through a certain environment, then that equals c. So frequency and wavelength are inversely proportional to each other. Now, just a note about equations. We are going to be dealing with equations in this course. Some of you may really not like math. I perfectly well understand that, but mathematics is the most elegant way to describe nature, be it physics, chemistry, astronomy, biology, whatever. Mathematics is a language which is beautiful in and upon itself. Difficult as hell to understand at times, but beautiful. What you will need to do in this course is to basically understand the relationships of those equations. Sort of be able to paraphrase what the equation is trying to say. So in this case, the relationship you want to know is with light. If the frequency goes down, the wavelength must go up. If the wavelength goes down, the frequency must go up. They are opposite in relation to each other. Again, we call this or conceptualize this light as an electromagnetic wave or a perturbation in the electric and magnetic fields which permeate the universe. Yada yada, that's all very technical sounding. Really what I want you to get out of is that we're going to get to something called the electromagnetic spectrum. And that is why it is called the electromagnetic spectrum, because the waves are electromagnetic, meaning they have properties of both an electric field and a magnetic field. Again, this is sort of just reiterating what I've already stated, that the velocity of an electromagnetic wave is set by the speed of light, and the speed of light is 3 times 10 to the 8th meters per second in a perfect vacuum. That is the ultimate speed limit as far as we know in terms of Einsteinian relativity. Nothing can move faster. Nothing can be communicated more quickly than something traveling at 3 times 10 to the 8th, or 300,000 meters per second. Light can slow down. You can actually force light to slow down, and light slows down once it's in denser media. If you shine light through air, that light is actually traveling slightly smaller speed than light traveling through a vacuum. Light traveling through water is traveling at an even slower speed than light traveling through air. Now, one of the fun jobs out there, for those of you who are physics minded, there are people out there who are, no kidding, trying to make light stop. They're trying to pull a Kylo Ren and stop a blaster bolt. They are trying to create a medium that is so dense or has properties that will actually cause light to have a velocity of 0. That is good as, all get out. So the electromagnetic spectrum, what is the electromagnetic spectrum? The electromagnetic spectrum is what encompasses all light. So as I said, light has a frequency and light has a wavelength, and they are opposite, they are directly related to each other. Frequency goes up, wavelength goes down, yada yada. I never said anything about the limits. How big can frequency get, or how long can wavelengths get? Well, as it turns out, infinitely long and short, long, high, low, and all of that infinite spectrum of light, of varying different wavelengths, varying different frequencies, that is what we call the electromagnetic spectrum. Now, only one part of that electromagnetic spectrum is defined via a physical basis, basically, rather than just say, well, it looks good if we just stop it here. And that is the visible part of the spectrum, and it is the smallest part of the electromagnetic spectrum that we have, or that we've defined. And it is set by the average width, as it were, or average wavelengths that the human eye can perceive, from red through orange to yellow, green, blue, indigo, and violet. Roy G. Biv. So that the rainbow of colors that you see, that is essentially the wavelength, all the wavelengths, all the frequencies of light that the human eye can distinguish. Red is of the longer wavelength. So red is the longest visible light that we can see. Blue, or violet, is the shortest visible light that we can see. Now, some people can see a little bit further into the red than others. They can actually technically look into the infrared. Some people can look into the ultraviolet, technically. But typically speaking, the range from 700 nanometers to 450 nanometers, that is what we define as visible light. Now, when you get to longer wavelengths, you get to infrared. And we normally think of infrared as heat, because when we think of night vision goggles or heat vision, what we're doing is we're looking in the part of the electromagnetic spectrum that is looking at things that radiate, just simply radiate heat. They don't emit light in the visible part of the spectrum, but they do emit a certain amount of lower energy light, which we refer to as heat. That is the infrared. Once we get to longer ones, we get into the radio, and the radio can be subdivided into microwaves, which are the shorter of the radio wavelengths, and then into just radio waves, which are the longest of the wavelengths. When we get into the higher energy, or shorter wavelengths, I should say, from visible we go to ultraviolet. Now, we're all fairly familiar with the ultraviolet in that it gives us tans. It causes tans, but it also can cause skin cancer. So thankfully, the atmosphere is rather opaque when it comes to ultraviolet light. Not completely. It doesn't block out all ultraviolet light, obviously, but it does block out enough that we can walk around without SPF 5000, plastered onto our skin. Then we get into the X-rays, and then we get into the gamma rays. X-rays we're familiar with in that we can see through bone, or we can see bone, we can see through human flesh and actually see what's beneath it. And then you have gamma rays, which unfortunately don't turn people into green rage monsters. They just kill them. But again, the atmosphere is almost entirely opaque to X-rays and is opaque to gamma rays, which again, thankfully, that allows life on this planet to exist. So, to summarize, if we are going in terms of wavelength, the longest wavelength is radio, then microwave, then infrared, then visible, then ultraviolet, then X-rays, and then gamma rays. That's from long wavelength or long wavelength, low frequency, to short wavelength, high frequency. So again, up and down. The other thing, and you may have picked it up in my terminology, frequency and a wavelength are related to energy. The amount of energy that a particular wave carries is based on its frequency. So radio waves are very low energy. So 5G, if you've ever heard anyone complained that 5G is going to vaporize you. Not exactly. You need a lot of X-rays in order to vaporize somebody, because each individual part, or each individual photon, or each individual wave carries a very minute amount of energy. Infrared carries a little bit more, visible carries a little bit more, ultraviolet X-rays and gamma rays, they carry a lot. That's why they are so harmful to us in small dosages, because they are so energetic. Now you might be asking yourself, if X-rays are so harmful, then, oh God, what happens the next time I break a bone? X-rays in small enough doses are perfectly fine. But if you're a technician and you're sitting there and you're giving X-rays one right after another, 24/7, well, man, 24/7, 40 hours a week, then yeah, you want to be behind some lead shielding, because that kind of exposure is bad over time. So this is all, again, talking about the different types of waves. Again, just to list them, we have radio going from low energy to high energy. We have radio waves, microwaves, X-ray, radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and then gamma rays. Pretty much covered this. So, as an aside, I know this is kind of really an aside, is called the Doppler. There's something called the Doppler effect, and we will talk more about what the Doppler effect is and how it is useful for astronomy momentarily. But we are most familiar with the Doppler effect actually in terms of sound rather than light, because in terms of light, the Doppler effect is so small in our ordinary usage as to be imperceptible without very fine equipment. But sound, not so much. So the idea behind the Doppler effect is, as an emitter of a wave travels, depending on the direction of travel, the waves in front of that vehicle, or in front of that emitter, are going to get shorter, and the waves behind it are going to get longer. And so that's going to, so if you remember the visible wavelengths, we have the longer wavelengths are red, the shorter wavelengths are blue. So if the wavelengths get shorter, then it becomes blue shifted. If the wavelengths get longer, they become red shifted. Now, in terms of sound, and again, what you're probably familiar with is if a siren goes by, what you notice is as the siren is approaching you, the pitch gets higher and higher and higher until it gets to you, and then as it moves away, the pitch drops significantly. It drops, and it drops more and more as the vehicle moves away. And so that is what we experience in terms of the Doppler effect, in terms of sound. In terms of light, what that means is if an object is moving towards you, the wavelengths get smaller, and therefore the light appears bluer. Again, this is a very small effect and not perceptible through the human eye on terrestrial origins. Basically, if I walk really fast towards a white light, it's not going to suddenly become blue while I'm doing it. I'm just not going to pick up enough speed to do it. Or if I move away from it, it's not going to become red. But when we start talking things like stars, now we're talking about things that are moving on the order of kilometers per second. And you can start seeing these effects noticeably using modern equipment. There was something else I wanted to say about Doppler effect, and I can't remember what it is. Going back to Einstein, whole relativity thing. So I've been talking about the idea of an object, which is an emitter, blue shifted, red shifted, depending on its depending on its motion. And Einstein would tell us that there is no absolute reference frame. There is no preferred place in the universe. And so really what the Doppler effect, when the Doppler effect occurs, is when either the source is moving towards you or you are moving towards the source. In either case, if you are approaching, if the distance between you and the source gets smaller, then the wavelengths get smaller, therefore it is blue shifted, the light becomes bluer. The opposite is if the distance between you and the objects, the emitter, are getting larger, that distance is getting larger, the wavelength is getting larger, and so therefore it appears redshifted. The Doppler effect is an amazing tool for finding out basically how things move, but only in a radial direction, only directly towards or directly away from us. If we want to know how an object is moving left or right or up and down, then we've got to get a little bit more creative. I've already really talked about this. Again, this is the equation which describes energy, and one of the things that I love most about physics is the fact that some of the most profound equations are the simplest. F equals ma, E equals mc squared, E equals hf. The energy of light is equal to a number called Planck's constant times the frequency of that light. So as frequency goes up, frequency of the light goes up, then the energy goes up. Or if the energy goes up, the frequency of that light goes up. And because frequency and wavelength are inversely proportional to each other, you can rewrite this equation such that E equals hc over lambda. Again, you're dealing with constants here. So basically you have that E, the energy, is proportional to 1 over the wavelength, or as the energy gets larger, the wavelength must get shorter, and so forth and so on. So how does light interact with matter? And that's really how we're talking about here is how does light communicate with us? How does it talk to us? Now it can basically do this through 4 different ways. Light can be emitted. Light can be basically shot off. Like a light bulb will emit light in order to illuminate a room. The sun will emit light through nuclear fusion to illuminate the space around it. It can be absorbed. The light can hit an object, and that energy can be absorbed by that object and transformed into something else. Some other form of energy, either heat energy, it heats up the object, or it causes the object to change phase, like it moves it from a solid object like ice to a liquid object like water. So it can be absorbed. It can also be reflected. It can be reflected off of a surface, and that is how we perceive color. So the pink in my shirt, well, let's go with the blue, it's easier. The blue in my shirt, the reason why you can see blue is, let's assume that the light in this room is white, that the light is emitting equally over all wavelengths in the visible spectrum. The reason why you see my shirt is blue, assuming that I got my settings right and you can actually see me at all, the reason why it's blue is because the shirt absorbs all of the light except for blue, and then it reflects that blue light to your eye. And those blue light photons, or that blue wave, hits your eye, gets absorbed again, and that information is then chemically processed to your brain, which tells you, oh look, blue, assuming you're not colorblind. Pink, again, is a combination of different wavelengths that you can see, so forth and so on. And so that's how you actually see things. If the light is not being emitted by the object itself, the reason why you can see it is because it is reflecting light. That is why when you turn the light off, when you basically cut out the emitter of light in the room, everything goes dark, because there is no more light to reflect. And then lastly, you can refract or disperse light, meaning that, and we're going to deal with this fairly extensively in the course, where when light travels from one medium to another, and again, medium is just a fancy word for environment. If the light goes from one environment to an environment that is denser or less dense, where the density changes, then it's going to cause that light to bend. It's going to the first slide was the cover of Pink Floyd's Dark Side of the Moon. If you caught that reference, good on you. A prism works by the fact that glass is denser than air. And so when white light hits that that glass, that light is going to be bent into its component colors, because red light is bent more than blue light. Or excuse me, blue light is bent more than red light, and so forth. And so it can disperse that, it disperses those colors so that we can see it. And Newton was the first person to really to experiment with this and actually write down his findings. He took a prism, shone white light through it, or sunlight through it, and he noticed a dispersal pattern that looked like the Roy G. Biv rainbow pattern, red through blue. And this is how we can look at light more specifically. Our ability to actually analyze light is enhanced by our ability to disperse it. Because white light, carries a lot of information. It carries blue light information, it carries red light information, orange light information. But what if we're only interested in the blue light? Or what if we're only interested in the red light? Before we can grab hold of that, we have to be able to disperse that light. We have to be able to separate it out so that we can look only, say, in the blue part or only, say, in the red part. This is, again, just a representation of an experiment that Newton might have put together. So a German by the name of Kirchhoff, many years after Newton, actually about 100 if I got my dates right, guy named Kirchhoff said, all right, there are basically three ways. Three ways you can get a spectrum. You can produce a spectrum. And those three different types of spectrum are called continuous, emission or bright line spectrum, or absorption or dark line spectrum. So a continuous spectrum is what you would expect from, say, a prism. Continuous spectrum means that the color is continuous from red to blue, or from long radio into short radio. It's a nice smooth curve going from one to the next. There are no sharp divisions in that spectrum whatsoever. The way to get a continuous spectrum is through a hot, dense object. So the object has, like, for example, incandescent light bulbs are producers of continuous spectrum. If you were to disperse the light using a prism or a modern-day spectrograph, which is what astronomers use, the tungsten in the filament gets very hot because of the electricity that's passed through it, and it's very dense because, well, it's tungsten, it's a metal. The sun also emits it also will produce, in its core, will produce a continuous spectrum, because, as you can imagine, it gets really hot in the sun's core, something like 10 million Kelvin. It's at that point, it's roughly 10 million degrees Fahrenheit. And it's real dense in the middle of the sun. So, very hot, very dense, produces a continuous spectrum. A bright line emission spectrum is produced by a hot gas that is not very dense, that is fairly rarefied. So certain types of nebulae, for example, will produce a emission line spectrum. Now, what is an emission line spectrum? What do you see in that? Imagine you take a continuous spectrum and you only take little bits of it. Basically, you cut out little lines from that rainbow pattern, and you display that. And so most of the spectra that you see is going to be dark, but you're going to have discrete red, blue, green lines running through that pattern. And that is due to a hot but less dense, or a rarefied gas. Now, an absorption spectrum is the exact inverse of an emission spectrum. Now, instead of getting rid of all of the light, or all of the spectrum except for those discrete little lines, you do the opposite. You keep everything but those little lines. So it would look as if you took a continuous spectrum and then cut out little black lines or little bits out of it, And those lines correspond both in the emission spectrum and in the absorption spectrum. Both of those lines correspond to very specific discrete wavelengths. And we'll come back to that. That is a very vital point when it comes to looking at spectrum, is that the spectrum produce lines at very specific wavelengths. Here is a schematic of what those lines actually look like. So again, you have the light source. It is shining. If you were just looking at the light source, it would produce a continuous spectrum, Roy G. Biv. Again, that the graph on the bottom is the intensity versus wavelength, or just how bright the light is. It's nice, smooth. It doesn't really vary sharply from one wavelength to the next. The emission spectrum is if you were looking at a cloud of gas which is illuminated by some sort of star or light source that you can't really see or is off to the side. The gas itself is not very dense, but it is heated up by the light of the star, and so we see an emission spectrum where we see basically bright blips, or if you were to look at that intensity versus wavelength, there are spikes in the intensity at very specific wavelengths. And again, the absorption spectrum is the inverse of the emission spectrum, where here the light is being, certain light is being absorbed or taken out of the continuous spectrum. Now, most of these are, most objects that we're going to be dealing with in astronomy, stars, galaxies, the like, when they produce a spectrum, they're going to produce absorption spectrum. Almost always, you're going to have a situation where you have a hot, dense core, and that light is being passed through some colder medium, or less dense medium, I should say. Not cold, but colder and less dense. So you have a really hot source, really dense source, passing light through a colder sort of layer of atmosphere, as it were, or a cloud layer, as it were. That is what produces an absorption spectrum physically. Again, going back to the dude Kirchhoff, these are the three types of things that allow us to, or the three physical situations that give rise to these three different spectra. So, what do we do with these? Like, why am I bringing up spectrum? Why is it important? Spectra are important because of the subfield of astronomy known as spectroscopy. Spectroscopy is the study of said spectra. Now, spectrum can be used to do all sorts of things, but there are two major ways that a spectrum can be used. One, it can be used to determine basically where in the electromagnetic spectrum is the light being emanated from. Is it primarily in the visible with a little bit in the infrared, or is it primarily in the ultraviolet with energy going all the way down through into the radio? A spectrum can also tell us how much energy the source is generating at each particular wavelength. So if you wanted to know how much light the object is producing in the blue as opposed to the red, you would use a spectrum in order to determine that. And you can, hopefully you saw through these graphs, particularly, let's look at A, the intensity in the indigo region is not as high as the intensity in the green region. And that tells us something very specific about the object in question, about that very hot, very dense light source. In general, when we talk about spectrum, we deal with things called black bodies or continuous spectrum. And they look like these. They basically look like if you go from high energy to low energy on a plot of intensity. So intensity goes up on the Y. Wavelength will decrease going to the right, or frequency will increase going to the right. Energy will increase going to the right in terms of light. And they look like in these black body spectrum, or continuous spectrum, will sharply rise in the high energy regime and then peak and then tail off in the low energy regime. And here you can see a family of curves. So couple of things. Here you see the region of light, which is the visible part of the electromagnetic spectrum. That is the part that we can see with the human eye. And so this graph primarily looks at a little bit of the ultraviolet, the visible, the infrared, and then the microwave and radio. And the other thing that you can see on here are a family of curves for objects with different temperatures, going from 2000 Kelvin to 500 Kelvin. To give you a sense of scale, a human body will produce a black body curve around 300 Kelvin, and the surface of the sun is around 6,000 Kelvin. So let's give you a sense of how hot things are, what a Kelvin is. Now, there are a couple of things you should be able to notice from this, from looking at the suite of curves. One is that the hotter the object is, the more energy it's generated at any particular time, what we refer to as luminosity, and we'll be coming back to that later on. A 5,000 Kelvin object, or an object with a temperature of 5,000 Kelvin, radiates more light everywhere than an object at 2,000 Kelvin. Then also, and that is defined by the Stefan-Boltzmann law. So L here is luminosity. That is the total energy being generated by an object every second. A is the surface area. Sigma is a constant. A is the surface area, so assuming that the body isn't changing in any way, that's also a constant. And then T is the temperature to the fourth power. So the total amount of luminosity, or the total amount of energy that is being generated by this object, is a function of temperature to the fourth power. It's a very steep function. So if you increase the temperature just a little bit, you're going to get, so for example, if you increase the temperature, if you double the temperature of an object, its luminosity goes up by a factor of 16. The other thing that you should be able to see from the suite of observation, or the suite of curves, is that the peak of where these curves occur changes depending on where it's located, or what the temperature is. And the peak of the curve is what we call lambda max, and that is equal to, again, a constant divided by the temperature. So let's go here. And what Wien's law, so Stefan Boltzmann tells us that the hotter an object is, the more energy that it produces everywhere. Wien's law tells us that the hotter an object is, the bluer that light is generally going to be. So for example, a 5,000 Kelvin object is going to appear yellow-green to the human eye. A 4,000 Kelvin object is going to appear red to the human eye. And then a 3,500 Kelvin object is also going to appear red, but it's going to appear brighter if you're able to look at it using infrared goggles. And then finally, the 2,000 Kelvin would also be in the far infrared. Now, the reason why we as human beings do not glow, again, as I said, the average body temperature for a human being is around 300 Kelvin. That means that we are generating energy. We have a luminosity. So why can't we see ourselves without a light on? And the reason for that is because most, if not all, of our energy is emitted in the infrared part of the spectrum. There is a minute amount of light being generated in the visible part of the spectrum, but we do not have the capability of detecting that few number of photons that is being generated from the human body at that low temperature. So almost all of the energy is being generated in the ultraviolet. So pretty much no energy is being generated in the visible part of the spectrum, which is why we need a light to reflect light off of the human body, as opposed to having the human body as an emitter of light itself. So again, just to recap, the hotter the body is, the more energy that it has. The hotter the body is, the bluer that is. And I know that may seem a bit counterintuitive because we're all used to our taps where you have red is hot and blue is cold. But if you've done any welding or have watched welding videos for some reason, you notice as the flame gets hotter, it becomes bluer. Stars radiate like black bodies. Not perfectly, but close enough for government work. And so when you look at a field of stars like this one, what we can immediately do is, just by looking at it, I can tell you that those bluer, greener stars are hotter than those redder stars. And you can also see by just looking at it, there are a lot more red stars than there are blue stars. And that tells us quite a bit about how stars are generated in the universe and where the mass of the universe is primarily located, at least the luminous matter that we have. Now, when it comes to spectra, we're going to kind of transition to emission spectra because it's easier to see. Now, one of the other things, probably the most, in my mind, kind of the most important thing about a spectrum is that the lines, both emission and absorption, these lines, like I said, occur at very specific wavelengths. And those wavelengths are dictated by the chemical element that is either doing the emitting or either doing the absorbing. So you can see here hydrogen, helium, mercury, and sodium. These are four particular types of elements. Hydrogen, when we only look at the visible part of the electromagnetic spectrum, has four lines. There is an indigo line, a violet line, a teal line, and a red line. Helium has a few more. The primary one is that yellow one. Mercury has a few more. That has what we call a yellow triplet, and then sodium only has two. Sodium light, that's why the old street lamps, they look orangey yellow, is because that's pretty much their sodium. They're under high pressure, and that's essentially what they only put out light in the yellow part of the spectrum. These are unique fingerprints. These are unique chemical fingerprints based on the element. No two elements emit or absorb light at the exact same frequency. And so we can use, if we can take get the spectrum of an object, we can look at the lines of that object and we can go to a catalog. Again, this is one of the things that we can do in the lab. We can take a hydrogen gas, we can make it really hot, and we can look at the spectrum of it and analyze what the lines are and catalog those. Really boring stuff, really, really important though. We could go to these catalogs and be like, all right, this star has hydrogen in it. Not only does it have hydrogen in it, 74% of it is hydrogen. This star has helium in it. It has 24% of the star is helium. And then it has a multitude of other elements which comprise the rest of the 2% of the composition. And we can identify, mercury is in a star by this much, sodium is in a star by this fraction, so forth and so on. Now, how do we really conceptualize this absorbing, emitting thing? Now that comes down to how do we conceptualize an atom? Because that is the atom of a molecule, and sometimes the molecule of a molecule, vibration of a molecule, which will cause light to emit or get absorbed. Excuse me. So we're going to start off with the wrong way to conceptualize it, but it's the easiest way. And that is the Bohr model of the atom. Now, an atom is composed of basically three components. You have protons, which are positively charged. You have neutrons, which have no charge, but have mass on the order of a proton. And then you have electrons, which are much less massive, but have exactly the same charge, just negative to the proton. So a proton has a certain amount of positive charge. The electron has the exact same amount of charge, but negatively oriented. And neutrons and protons are about the same mass, but neutrons, again, do not have any charge. A cluster of protons and neutrons corresponds to the nucleus of the atom. That is a central part of the atom, and depending on the number of protons, that dictates what the chemical species is. So, for example, hydrogen has 1 proton in its nucleus. Hydrogen has 2, lithium has 3, beryllium has 4, and so forth and so on. And no, I don't know what 5 is. I'd have to look that up. That's why God created the periodic table. Anyway, so the number of protons it determines the chemical species of an element. Also, as you go up in protons, you also go up in electrons. The hydrogen atom has 1, the helium atom has 2. Unless you're talking about weird isotopes or what have you, you have basically twice as many electrons as you do protons. Now, the reason why I call this the wrong way of conceptualizing this is the Bohr model of the atom, well, kind of the Bohr model of the atom, in the sense that Niels Bohr thought of the atom as a mini solar system, where the nucleus was at the center of this thing, center of the atom, and electrons orbited around the nucleus in these very discrete orbits, or basically flat orbits. The only thing he added, the only difference between the atom and the solar system, is that a planet can orbit at any distance from the sun. In an atom, because of what Planck realized, and that energy is quantized, atoms can only, or electrons can only orbit at certain distances away from the nucleus. All of the other distances are forbidden. In reality, what we have is more complicated, and you can thank quantum mechanics for that, because quantum mechanics hates everyone. What you have is you have a nucleus. The proton and neutron is in the center of this thing, and then the electron is in some form of cloud, probability cloud, surrounding it. Now, what I mean by probability cloud is there's something called the Heisenberg uncertainty principle, which, if you think about it too much, your head will explode. I've seen video footage of this. What it states is that you cannot know precisely the location and velocity of an object. The more you know of one, the less you know of the other one. So if you know how fast something is going, then you have no idea where it's located, and that's where that probability cloud comes in. Is we can measure fairly accurately the velocities of these electrons as they orbit around, or as they move around the nucleus. But that means we really have no idea where that electron is at any particular point in time. We just know that it's more than likely in this sphere. Now, where that translates to orbital size, in the sense that if you go back and you can see here, you have 4 different orbits. You have orbit 1, which would be the ground state. You have orbit 2, which is the first excited state. Orbit 3, orbit 4. That would just correspond to the size of the cloud. The higher the orbit in the Bohr model, the larger the cloud we're talking about in the quantum mechanical realm, in the or the modern standard model. So, as I said, we're going to continue to talk about it in the Bohr model, because that makes things easier, and I like things that are easier. We're going to talk about the fact that electrons can only exist in certain orbitals. They can only exist at certain distances from their host proton, the proton they're bound to. And this is what we mean by quantized, that it's not a continuous range where the electron can exist. It can only exist at very discrete locations. And all other in-between locations are forbidden. Each of these orbits are referred to as an energy level, or an energy shell. So if an electron is sitting at the ground state, then that electron has a certain amount of energy, but it has the lowest amount of energy that is physically allowed for that element. So a hydrogen atom with an electron just sitting in the ground state is just sitting there with 13.2 electron volts worth of energy, which, trust me, ain't a whole lot. But if you were to impart a little bit of energy to it, now, backing way off, and I may actually cut that out for editing because that's just completely wrong. All right, let me start this over again. You have an electron sitting around the proton. It's basically sitting in a very low energy state, but not the 13.2 that I was talking about. If a photon comes by with a particular energy that the hydrogen atom likes, then what's going to happen is that hydrogen atom is going to absorb that energy and is going to bounce that electron up to a higher energy state. This I am certain of. If a photon with an energy of around 10 eV, which again, not much energy, but if it's around 10, not 9, not 11, but 10, 10.7, I think, if it hits with that very specific amount of energy, that energy is going to get absorbed, and it's going to bounce that electron up to a higher energy state. Now, the other things I love about the universe is lazy. The universe wants to have as little energy as possible. I can get behind that. And so very, very quickly, that electron is going to fall back down towards the center of the atom on the couch that it really likes. And so when it does so, it goes from a high energy state to a low energy state. And if because of the fact that energy cannot be created or destroyed, that a photon will get shot out into space. It will create light. So let's imagine, and this is how dispersion or refraction kind of really happens, is that you have light, or scattering. It's scattering. You have an electron, or you have an atom sitting there, coming in from, I guess that would be your right. I don't know how this is arranged. Coming in from the side, it hits the photon hits this thing and gets absorbed, pops up the electron, and then very, very quickly, we're talking fractions of a second, the electron falls back down and emits an electron, or emits a photon of the same amount of energy. There's a caveat to that, which I'll explain in a second. That photon gets emitted in a random direction. It can go up, it can go down, it can go over here, it can go that way, wherever, in a random direction. Or really minute possibility, it could actually get shot off in the same direction that it came from. But that's a very, very rare possibility. Now, the caveat that I want to make is that in this scenario, you have an electron in the ground state, gets hit by a particular photon with particular energy, gets bounced up to the first excited state, and then falls back down to the ground. That will absorb. So in that case, the photon which is emitted it has the same amount of energy as a photon getting absorbed. And generally speaking, that is a truism. That is going to happen. That the energy that is absorbed by an atom, or the energy that is emitted by an atom, must equal the energy that is absorbed by the atom. Again, energy cannot be created or destroyed. But if you're talking about, if you increase the amount of energy that you send to this photon, you can bounce it from the ground state up to, say, the second excited state, or the third excited state, or what have you. When you do that, the electron can come down. It can come straight down. It could go straight back down to the comfy couch, or it can meander. It could go to the fridge and get down to the second excited state. Go over to the TV and change the channel. Talk about the first excited state, and then back to the couch. So it can cascade. So if it goes directly down, then the incoming photon and the outgoing photon are exactly equal. But if it bounces around, if it takes a while to get back down, or if it takes its time to get back down, then if you add up all the energy of the outgoing photons, that has to equal the incoming energy of the photon that was absorbed. And that's what this is basically telling us. And so that is why the spectrum is a chemical fingerprint, because those lines correspond to, well, I should back that up a little bit and say the reason why there are the spectrum are chemical fingerprints is because each atom is unique in terms of the size of the energy shells. So the ground state for the hydrogen is at a different energy than the ground state of a helium. The first excited state of a hydrogen is at a different energy than the excited state for helium, so forth and so on. So depending on the element in question, you have different absorption. You have different lines that can be produced. And so the transitions which lead to spectrum, again, a hotter gas is going to give off an emission spectrum. Basically, the idea is that that hot gas has been heated up by some external source, which is not immediately apparent, and then it's gonna that energy is going to get released because those electrons are going to fall back down to ground states, and then collisions, actually gravitational interactions between the atoms, can also provide a certain amount of energy to re-excite those atoms or those electrons back up, so that they will emit again at particular wavelengths, which correspond to the chemical species of that atom. Absorption spectrum come from the fact that you have, like I said, a hot, dense source, continuous source, putting light out at all wavelengths. That light passes through a colder material and will absorb some of that incident photon. So almost all of the elements, all of the electrons in that cloud are nice and comfy on their couches, and then this light gets pumped in and knocks them all off their couches, and they try to get back down. And they send light scattering in all directions, which is why we look at it when we're on directly the opposite side. That's why it appears like it's being absorbed. Because as I said, when missing or black, we're not seeing the light at all, because the light, when it comes in, it gets absorbed and then it gets re-emitted into any direction, and it's only very slightly probable that it goes in the same direction that it was traveling and can actually be detected by us. More than likely, it's being shot off into some random part of space. And so here again, you can see that the particular lines, so the red line, for example, corresponds to the electron going from, let's see if I get this right, the fourth level to the, actually I can show you right here. So the red line corresponds to 3, the electron going from level 3 to level 2. The green line goes from level 4 to level 2, and these are what we call the Balmer lines of the electromagnetic spectrum. Really, again, after the guy who originally discovered them. Main takeaway, these lines occur at very specific wavelengths because they are dealing with very specific transitions. Again, this is what we're called you can look at n equals 1 is one orbital, n equals 2 equals another orbital, and so depending on the transition, how the electron moves, that will give you a very discrete amount of energy, either emitted towards you or absorbed, so that you cannot see it. Now, what does this have to do with the Doppler effect? Now, coming back to the Doppler effect, we have is if the object is at rest in relation to you, again, all things are relative. If the distance between you and the emitting object is not changing over time, then you would see hydrogen exactly as you would see it in the lab. You would see the red line at 656 nanometers, the blue line around 500 nanometers, or the teal line around 500 nanometers, and so forth. But if that object is moving away from you, if the distance is getting larger with time, then you will notice that these lines are red shifted. They will have shifted to the red part of the spectrum. If the velocity is constant, then it's a constant shift. Then it goes from, say, 556 nanometers to, 656 nanometers to, say, 660, and it stays there if the velocity is constant. If the velocity changes, then depending on the size of the velocity, depending on the size of the velocity, that's going to dictate the size of the shift. So, a star that is moving further away, or a star that is moving away from you faster, the red lines are going to be, the lines are going to be red shifted larger than a star that is moving away from you at a smaller velocity. So a higher velocity is a larger shift, a lower velocity is a smaller shift. And commensurately, if the object is moving towards you, or if you are moving towards the object, if the distance between you and the object is shrinking, then the lines will become blue shifted. The object will be slightly bluer than it was if it's at rest. Now, like I said, that can tell us the velocities of things or how things are moving. So if you can get a spectrum of something, already you can tell certain things. You can tell its temperature. You can tell how hot it is. B, you can tell how much what the composition of that object is, at least to first order. And then C, you can see whether or not how that object is moving, and not just whether or not that object is moving away or towards you, but in certain cases, you can actually determine whether or not that object is rotating. So if you have a star, even if that star is sitting at a constant distance away from you, if that object is sitting at a constant, or if the distance to that object is constant, because it's rotating, one half of the star is moving towards you, the other half of the star is moving away from you. So if your instrument is precise enough, you can actually get see the light from the left-hand side, for example, that's moving away from you, get red shifted, and the light from the blue-hand side get blue shifted and move towards you. You can definitely see this for extended objects like galaxies, and we can use that information to determine things like how far away it is. And we'll get into all that. So spectrum are exceedingly useful. Like I said, right off the bat, you can get the temperature of the thing, you can get the chemical composition of the object, and you can tell how fast it's moving or away or towards you, or even if it's rotating in some cases. All right, and that is all for today. So we talked about light. Really hope you can see me other than just looking at a black screen. We talked about light, and next time we're going to talk about how we talk to light. We're going to talk about telescopes. We're going to I don't know how far I can throw this analogy or beat this analogy with like a dead horse. We're going to talk about telescopes. We're going to talk about what are the tools that astronomers use to actually measure these or collect this light, analyze it, and come to the conclusions that we do surrounding it. We're also going to talk about what the atmosphere does to the light, and why the atmosphere is a challenge to astronomers on the ground, and why we want to send up space telescopes like Hubble in order to mitigate the effects that the atmosphere has. All right. So I will see you all next time.